In this section, I will explain the voltage distribution across the string efficiency, that is n number of discs are connected in series, that is represent for the string there. How the voltage is distributed from individual the disc, that is one end is connected for the conductor, the another end is connected for the supporting structure. How the voltage is distributed? For example, we can take three insulators are connected in string. That is, what is the disk 1 voltage, disk 2, another one is for the disk 3 voltage. That is the suspension type insulator, the another name is represent for the disk type insulator. And next topic is methods of improving string efficiency. That is voltage distribution across the string efficiency, or another name it is represent for voltage distribution across a string of suspension insulator. That is how the voltage is distributed in a string of insulator. That is here in the transmission line, we are used for suspension type insulator or disk type insulator. Based upon the operating voltage, we are connected for n number of discs in series. Already the last class we have discussed. For example, you can take 400 kV transmission line. How many number of discs are connected in series? That is the formula is there. That is you can substitute the phase voltage by individual disc capacity plus one additional disc or spare disc, that is for phase voltage, that is 400 by root 3, that is 400 kV is the line value, 400 by root 3 is phase value. The individual disc capacity is 11 kV plus one additional disc or spare disc, that is we are getting approximately equal to 22 discs are connected in series. 22 suspension type insulators are connected in series for 400 kV transmission line. The material used is porcelain material or toughened glass material. Similarly, you can consider for any level of the operating voltage, that is 66 kV, 132 kV, 220, 400, and then 765 kV. For any operating voltage level, they are considered for the same formula. Now here, based upon this number of discs are connected in series, how the voltage is distributed in a string of insulator. That is voltage distribution across the string efficiency, or it is represent for voltage distribution across suspension insulator, that is string of suspension insulator. Now here in this the example, the supporting structure they are taken for the pole, and the suspension type insulator is connected for horizontal plane. That is here the considered the supporting structure is pole or tower. The suspension type or disc type insulator is connected in the horizontal plane. Here number of discs are connected is, that is 4 discs are connected, and this is disc 1, disc 2, disc 3, disc 4. One end is connected for the conductor, another end is connected for the cross arms. That is a string of suspension insulator consists of n number of discs based upon the operating voltage. It is connected with the help of metallic link. That is one disc to another disc in between, that is we are connected with the help of metallic disc. And here, that is in between one disc to another disc, it acts as a capacitor. That is the capacitor, it consists of two parallel plates without any electrical link between. That is in between the mutual is there is no connection is there in between the two parallel plates. Similarly, from one one insulator to another insulator, it is act as a capacitor. That the capacitance is known as the mutual capacitance or self capacitance. This capacitance, that is the insulator in between the insulator act as a capacitance. That capacitance is represent for mutual capacitance or the self capacitance, that is represent for MC. But the practically this supporting structure to insulator in between act as a isolation medium, that is act as a capacitance. This capacitance is represent for shunt capacitance, that is represent for C. Now let us consider, that is we have taken the example is 4 the discs are connected in series. That is one end is connected for the conductor, the another end is connected for the supporting structure, that is cross arms. Now The in between the disk act as a capacitance, that is represent for self capacitance or mutual capacitance, that is represent for MC, and supporting structure to insulator, the act as a capacitance, that is represent for shunt capacitance, that is represent for C, that is represent for C. Here the disk 1 nearer to the cross arm side, that is represent for the voltage 1, the next voltage 2, voltage 3, voltage 4, so on, etc. That is starting from the cross arms and ending to the nearer to the conductor side. The total in a string voltage or the strip voltage is represent for voltage. It consists of the 4 disks. Individual the disk voltage is represent for V1, V2, V3, and then V4. It is started from the supporting structure, that is cross arm side, that is cross arm V1, V2, and ending nearer to the conductor side. Now, in between, that is one disk to another disk, act as a capacitance, that is mutual capacitance or the self capacitance, that is represent for MC. And cross supporting structure to insulator, act as a capacitance, that is represent for self capacitance. That current is represent for IA, IB, IC, and then ID. Here, what about the voltage up to now? V1. Here, what is the voltage? Adding both, that is V1 plus V2. Here, what about the voltage? Adding all the individual disk voltage, that is V1 plus V2 plus V3. Here, what about the voltage? Adding all the voltages, V1 plus V2 plus V3 plus V4. And the self current or the mutual current is represent for I1, I2, I3, and then I4. Here we want to find out the individual, how much the voltage, that is all the disk, it should be maintained for same voltage or it should be different. But already the last class we have discussed, it is not maintained for the equal voltage. That is, once we are deriving means the which side the voltage is maximum, that is conductor side or cross arm side, and which side the voltage is minimum, which side the voltage is minimum. That is, let us consider the C is represent for the ground capacitance, or else it is represent for shunt capacitance. C is represent for ground capacitance or shunt capacitance. Act in between, that is supporting structure to insulator. Act in between the supporting structure to insulator. And MC is represent for mutual capacitance or self capacitance, that is in between the insulators, that is one insulator to another insulator, that is act as a self capacitance or mutual capacitance, that is represent for MC. And V is total strip voltage or total string voltage, total strip voltage or total string voltage. And V1, V2, V3, V4 are the individual disk voltage, that is individual insulator voltage. And V1 is connected nearer to the cross arm side, and V4 is connected nearer to the conductor side. But here we are taken for the example is 4 insulator are connected in a series, that is represent for the strip. V in the sense the total voltage of the string, that is all the combination, how much the voltage considered for the 4 insulator. And individual the disk voltage or individual insulator voltage is represent for V1, V2, V3, and then V4. Now consider this diagram, that is consider this diagram. From this diagram, what is the current I1, and I1, I2, I3, I4 is current considered for the self current or the mutual current, and IA, IB, IC, ID is represent for the shunt current. Now that is I1 is what happened, weight of the conductor W, and what is the capacitance? This is represent for the mutual capacitance, that is represent for MC. What about in this the disk voltage is V1, that is WMC into V1. Next we can write down IA, that is weight of the conductor, it is represent for W, and what is the capacitance value? That is the shunt capacitance, the C, and what is the voltage here? V1. Now here the apply Kirchhoff's current law, that is the junction point is the sum of current towards the junction point is equal to sum of current leaving the junction point. What are the current towards the junction point? I2 is towards the junction point, and IA and I1 is away from the junction point. If you are applying the Kirchhoff's current law, that is I2 equal to IA plus I1, I2 equal to IA plus I1. Already we know the value of I1. What is I1? WMC into V1. What is IA? WC into V1. The substitute here, that is WMC V1 plus WC V1. In this the both the term, that is WCV1 and WCV1 is common. You should take common WCV1. What happen? That is 1 plus M. This is the I2 value. Now, what is the voltage V2? That is V2 equal to parallel across the current is I2. That is, this is capacitive reactance, that is represent for XC. Inductive react is represent for XL. That is, XL is 2 pi FL and XC in the sense 1 by 2 pi FC. 1 by 2 pi FC. That is voltage, that is V2 equal to across the current I2, that is the capacitive reactance is represent for XC. Already we know that what is the XC? XC is represent for, that is XC is represent for 1 by 2 pi FC. What is the 2 pi F? That is omega C. But here, that is the capacitance. Here we are considered for the self capacitance or mutual capacitance. The substitute here, that is I2 into 1 by 2 pi F in the sense omega. The capacitance is substitute for the mutual capacitance or self capacitance, that is represent for MC. That is I2 into 1 by W into MC. This is the V2 value. Now, already we know the value of I2 value. What is I2? The substitute here. That is WCV1 into 1 plus M by W into MC. That is numerator W, denominator W, numerator C, denominator C gets cancelled. That is, finally we are getting 1 by M into V1 into 1 plus M. V1 into 1 plus M. That is, you can see here, that is, if you are substituting, we are getting V2 equal to V1 into 1 plus 1 by M. That is, here we are getting V1 by M into 1 plus M. You can send this the M internal, that is V1 into 1 by M plus M by M. If you are taking the LCM is common, M means the value is not changed. This gets cancelled, numerator and denominator. So finally, we are getting V2 equal to V1 into 1 plus 1 by M. This the term we are getting for the one, that is 1 plus 1 by M. And now we can write down similarly. What is the IB current? That is IB equal to weight of the conductor W. This is the shunt capacitance C. What is the voltage? V1 plus V2. That is IB equal to V1 plus V2 into WC. And that is V1 plus what is the value of V2 value? Already here is that. That is V1 into 1 plus 1 by M into WC. Here in this the two term V1 is common. You should take common V1. What happened? WC V1 1 plus 1 by M. That is, you have taken V1 common means that is 1 plus this V1 is also already you have taken common 1 plus 1 by M. Now what happened? 1 plus 1, that is WC V1 into 2 plus 1 by M. This is the IB value. Now already we know the value of I2 and then IB value. Now apply the Kirchhoff's current law. That is, sum of current towards the junction point is equal to sum of current leaving the junction point. Now towards the junction point is I3, leaving the junction point is IB and then I2. Now apply Kirchhoff's current law. That is I3 equal to IB plus I2. What is the IB current value? That is WC V1 into 2 plus 1 by M. What is the I2 value? Already you have derived here. That is I2 equal to WC V1 into 1 plus M. Now the substitute here, that is IB is WC V1 into 2 plus 1 by M and I2 is WC V1 into 1 plus M. Now in this the two term you should take common, that is WC V1 is common. If you are taking common, what happened? That is WC V1, if you should take common, that is 2 plus 1 by M plus 1 plus M. Now that is WC V1 into What is that? Is 2 plus 1, that is 3 plus, that is 3 plus m plus 1 by m. This is the value of I3. You can check here, that is taking WCV1 is common, 2 plus 1 by m plus 1 plus m. Finally, we are getting I3 equal to WCV1 into 3 plus m plus 1 by m. Now we know the value of I3. Next, we can voltage the across V3. What is V3? Across the current I3, the capacitive reactance is XC. That is I3 into XC in the sense 1 by 2 pi FC. 2 pi F is omega. This capacitance is self or mutual capacitance. That is represent for MC. That is I3 into 1 by omega into MC. Now that is I3. What is the value of I3? WCV1. WCV1 into 3 plus m plus 1 by m. WCV1 into 3 plus m plus 1 by m divided by W into MC. The same here, the numerator denominator WC gets cancelled. So finally, we are getting, that is V1 by m into 3 plus m plus 1 by m. The send m internally, that is V1 into, if you are sending m is internal, that is 3 by m plus m by m plus 1 by m into m square. That is the finally we are getting, that is V3 equal to V1 into this numerator and denominator gets cancelled, that is 1 plus 3 by m plus 1 by m square plus 1 by m square. Now check it here, that is substitute the I3 value, WCV1 into 3 plus m plus 1 by m, numerator and denominator WC gets cancelled, that is V1 by m into 3 plus m plus 1 by m. If you send internally, that is m means we are getting V1 into m by m gets cancelled, that is 1 plus 3 by m plus 1 by m square plus 1 by m square. Now this is, we are getting V3 equal to V1 into 1 plus 3 by m plus 1 by m square. Now apply Kirchhoff's current law, that is, what is IC? Next we want to find out I4 current. I4 equal to IC plus I3. Already we know the value of I3. We want to find out IC. What is IC? W into weight of the conductor into shunt capacitance C. What is the voltage? V1 plus V2 plus V3. That is IC equal to V1 plus V2 plus V3 into WC. And that is, what is V1 is the same, WC into V1. And what is the value of V2? Here, that is IC equal to, that is IC equal to V1 plus, what is the value of V2? What is the value of V2? That is V1 into 1 plus 1 by m. V1 into 1 plus 1 by m. What is the V3 value? That is V1 into 1 plus 3 by m plus 1 by m square into WC. Here V1 is common. Here V1 is common. V1 is common. You should take common V1. That is WC into V1. That is, you should take common 1 plus this value. That is 1 plus 1 by m, and this term, that is 1 plus 3 by m plus 1 by m square. 1 by m square. That is WCV1 into, what happened? That is 1 plus 1, that is 2 plus 1, 3. That is 3 plus 1 by m plus 3 by m. Now adding, what happened? That is 4 by m plus 1 by m square. This is the value of IC. It is WCV1 into 3 plus 4 by m plus 1 by m square. that is WC IC equal to WC V1 3 plus 4 by M plus 1 by M square. Now we can apply the Kirchhoff's current law. Now once we are applying the Kirchhoff's current law, what happen? Same, that is apply Kirchhoff's current law here. That is I4 equal to IC plus I3. What is the value of I3? WC V1 into 3 plus M plus 1 by M. What is the value of IC? Now we have find out, that is WC V1 into 3 plus 4 by M plus 1 by M square. That is IC value plus I3 value. The both the term you should take common WC V1. That is we are getting WC V1, that is 3 plus 4 by M plus 1 by M square. Now here you can consider, that is if you are taking common is WC V1, that is 3 plus 4 by M plus 1 by M square plus 3 plus M plus 1 by M. Now here what happened? WC V1 into, that is 3 plus 3, that is 6 plus the M value plus 4 by M plus 1 by M, that is 5 by M plus 1 by M square plus 1 by M square. This is the I4 value. Now the voltage, that is V4 equal to across the voltage I4 into XC, that is I4 into 1 by W into MC. Now what happened? Already we know the value of I4 value. Substitute here, that is WC V1 into 6 plus M plus 5 by M plus 1 by M square, the denominator by WMC. Numerator and denominator WC gets cancelled. Now the finally we are getting V1 by M into 6 plus M plus 5 by M plus 1 by M square. Now the considered, that is V4 equal to V1, this the M is goes to the internal. Now we are simplifying what happened, that is the 6 by M plus V1 into 6 by M plus M by M plus 5 by M into M square plus 1 by M square into M, this M cube. Now that is V1 plus numerator and denominator gets cancelled. 1 plus 6 by M plus 5 by M square plus 1 by M cube. This is the value of V4. Now considered the parameter V1, V2 and then V3. The V1 as it is for the V1. And what is the value of V2? That is the V2 is V1 into 1 plus 1 by M. That is V2 equal to, that is V1 is V1 and V2 is V1 into 1 plus 1 by M. For example, you can take V1 equal to 10 volt. V1 equal to 10 volt. This the 1 plus 1 by M term is 0.5. That is what happened? 10 into 0.5. Again, the multiplication means the term is increased. The term is value is increased. That is V1, V2 value is higher value, V1 value is the lower value. Again, what is the V3? Now you can see here, that is V3 is V1 into 1 plus 3 by M plus 1 by M square. Again, the term is increased. And what about the V4? V1 into 1 plus 6 by M plus 5 by M square plus 1 by M cube. Again, the value is increased. That is V4 is greater than, V3 is greater than, V2 is greater than V1. That is V4 is connected to the conductor side and V1 is connected to the supporting structure, that is cross arm side. Now the conductor side, the insulator, the voltage is maximum and goes on decreases toward the supporting structure. That is V4 is higher value comparing to V3 and V3 is higher value comparing to V2 and V2 is higher value comparing to the V1. That is V4 is connected to the conductor side and V1 is connected to the supporting structure cross arm side. Now what about the total, the string voltage or strip voltage? That is total string voltage or strip voltage equal to V1 plus V2 plus V3 plus V4. that is the total individual disk voltage is represent for total string voltage or total strip voltage. Now from this the derivation, clearly we know that the V4 is the higher value comparing to V3, and V3 is the higher value comparing to V2, and V2 is the higher value comparing to the V1, and these are not maintained for the same. Now here we want to find out the string efficiency. Already we have studied the string efficiency is defined as the ratio of voltage across whole string divided to the product of number of disk into voltage across the disk nearest to the conductor into 100. Here, what is the voltage across the whole string? That is the string voltage or the strip voltage, V by N. That is number of disks connected in series. In this example, how many number of disks are connected in series? That is 4 disks are connected in series into voltage across the disk nearest to the conductor. The which voltage is nearest to the conductor? V4. That is V4 into 100. That is the string efficiency is V by number of disk N, that is 4 disks are connected in series into voltage across the disk nearest to conductor V4 into 100. This is the voltage distribution of string efficiency or voltage distribution across a string of suspension insulator. In this derivation, it clearly shows that all the disk in a string of insulator is not maintained for the same voltage. That is nearer to the conductor side, the voltage is maximum, and nearer to the cross arm side, it is minimum. That is V4 is greater than, V3 is greater than, V2 is greater than V1. That is nearer to the conductor side is maximum and goes on decreases towards to the supporting structure side. And the next topic is methods of improving string efficiency. Now here the string efficiency is reduced because different the insulator is maintained for the different operating voltage. Due to that, the string efficiency is not maintained for constant. It should be either reduced or increased, or it is not maintained for the constant. But practically in transmission line, the string efficiency is the lower value. How we can improve the string efficiency? There are 3 methods are there. One is by using long crosser or eliminating the ground capacitance, and another one by using the insulator or capacitance grading, and the third one by using guard ring or static shielding. The first one by using longer cross arm or eliminating the ground capacitance. The ground capacitance is represent for the shunt capacitance. Shunt capacitance, that is represent for the C. Now the value, that is the shunt capacitance value is reduced means, and the string efficiency is decreased. The string efficiency is increased. Now for example, you can take, this is the supporting structure tower is there. Now in between, this is connected for the insulator, that is based upon the operating voltage, number of disks are connected in series. Here act as a ground capacitance or the shunt capacitance. In between the disk act as the mutual capacitance or the self capacitance. Mutual capacitance or self capacitance. That is by using longer cross arm. Suppose this the cross arm, it should be extended. That is increasing by reducing the value of this value, that is the shunt capacitance value. At that time, we can increasing the string efficiency. But the shunt capacitance can be decreased by using long cross arms. But practically, it should be maintained. That is as per our standard, as per our wish, we can't able to increase the shunt capacitance value. But as per the ratio, that is the ratio of the mutual capacitance, the ratio of mutual capacitance to the shunt capacitance, the value is never exceeded the 10. That is the mutual capacitance to shunt capacitance. That is the mutual capacitance is represent for MC and the shunt capacitance is represent for C. Numerator and denominator gets cancelled. The ratio never exceeded the value 10. That is either it should be value is for either 4 or 5, 6 or 10. Never exceeded the value 10. Like that, we need to design the cross arms. By using longer cross arms means once the cross arms it should be increased means, that is the value of the efficiency is increased. That is decrease the value of the shunt capacitance, the value of string efficiency is increased, but never exceed the value 10. How we are considered means, that is the ratio of the mutual capacitance to the shunt capacitance, the value never exceeded for the 10. And the next one, by grading the insulator, otherwise it is represent for the capacitance grading. Now in this method, we are taking the insulator different dimensions, and once we are using different dimensions means automatically the capacitance value is also different. But here one more drawback is that it is practically it is not applicable. Once we are taking different size of the insulator, that is which one is connected to the cross arm side and which one is connected to the conductor side is also some ambiguity is available, but practically it is not applicable. Once we are choosing different types of insulator, that is nearer to the conductor side, the voltage is maximum and goes on decreases to the supporting structure side. Now the supporting structure side, the disc, the larger size disc is connected and goes on, the size is reduced means at the time the string efficiency should be maintained constant, but practically it is not applicable. And the third one is by using guard ring or the static shielding or static shielding. This is the guard ring or the static shielding. One is represent for the insulator to insulator, that is the mutual capacitance or self capacitance, that is represent for the MC. The current is represent I1, I2, and then I3, I4. And one supporting structure to insulator, that capacitance is act as a shunt capacitance. Current is represent for IA, IB, and then IC. Now the bottom of the insulator, that is nearer to the conductor side, we are connecting the ring, that is nothing but represent for the guard ring. Now we are adding the current IX, IY, and then IC such a way that the shunt capacitance current is equal. Now the metallic fitting at the time, the capacitance value it should be balanced. This method is applicable for practical, that is by using the guard ring. This method is applicable to improving the string efficiency, but this method it is not applicable by grading the insulator. But this it should be followed somewhat. But one condition is that never exceeded the ratio, that is 10, that is the mutual capacitance with respect to the shunt capacitance, that is the CC gets cancelled, the value never exceeded the 10. These are the various methods improving the string efficiency, but practically it is applicable for first method and then third method. Third method is used for the all level of the transmission voltage, but is used for 220 kV, 400, and then 765 kV. And the last topic in the overhead line insulator, that is need of arcing on and then guarding. What is the necessity of the connecting the arcing on and then guarding? Generally, the insulators are the failure due to the puncture and then the flashover. Once the puncture is appeared, that is appeared in between the conductor and then insulator, the voltage is not maintaining for the balanced. The fully voltage is not operated. And the puncture means that is once flashover is taken place, it flows through the earth through the body of the insulator. At that time, the complete insulator is failure. To avoid that one, in that the overhead transmission line, the insulator itself they are placed for the arcing on and guard ring. The guard ring is connected nearer to the conductor side, and arcing on is connected nearer to the supporting structure side. That is, the top portion is connected for the arcing on, and the bottom portion is connected for the guard ring. That is to protect the insulator from the flashover and the puncture. That is the guard ring and arcing on is employed. That is, the top portion is connected for the arcing on and the bottom portion is connected for the guard ring. That is, the arcing on is fixed at the top of the portion that is nearer to the supporting structure side to protect the flashover, and the guard ring is connected nearer to the conductor side to protect the puncture. That is, because we are using the insulator, the cost is more and the lifetime it should be high. For that purpose, to protecting of the transmission line, we are used for arcing on and then guard ring.